Okay, sorry about the interruption. We're having difficulties with technology today. I think there's some inclement weather that's affecting utilities, so I'll keep going as best I can. So still on the topic of mean value theorem. The mean value theorem can be interpreted as saying there's a number at which the instantaneous rate of change is equal to the average rate of change over an interval. Okay, and that's just because the slope of the tangent line at some number is the same as the slope of the secant line connecting the endpoints of the interval. All right. So yeah, so we can obtain information about a function from information about a derivative. Okay, so let's see what the next example is. Oh, okay. Yeah, so suppose that f of 0 is equal to -3 and f prime of x is less than or equal to 5 for all x. How large can f of 2 be? And of course, we don't know what f is. All we know is these constraints for the function. All right. So, so we're given that f is differentiable and therefore it's continuous. Okay. Remember the theorem from chapter 2. A differentiable function is always continuous, but not vice versa. So because it's differentiable and it's continuous, we can apply the mean value theorem on the interval 0 to 2. And why is it that we want to do that? Because we want to know how large f of 2 can be. So let's see, what else do we have here? Yeah, we have f of 0 is -3, and we want to know the maximal value of f of 2. Okay, so the mean value theorem says that f of b minus f of a is equal to f prime of c times b minus a. So solving for f of 2 must equal to f of 0 plus 2 times f prime of c. F of 0 is -3 plus 2 prime of f of c. Now we know that the largest value of f prime of c is 5 because we were given f prime of x is always less than or equal to 5. So we can plug in the largest value for f prime of c to get the largest value of f of 2. Okay, so here we go. 2 prime of f of c is always less than or equal to 10. So f of 2, which is equal to -3 plus 2 times f prime of c, must be less than or equal to -3 plus 10, which is 7. So therefore, the largest value of f of 2 is 7. All right, so NVT can be used to establish some basic facts of differential calculus. So we have, all right, so here's a consequent of the mean value theorem. If the derivative of a function is equal to 0 for all x in an open interval a to b, then f is a constant. Okay, so we've already demonstrated that by finding the limit of the difference quotient. No need to do that. What else? Let x1, x2 be any two numbers, and a and b with x1 less than x2. So if f is differentiable on the open interval, it must be differentiable on the subinterval in a to b and continuous on the open interval. Yeah. Okay, so what this means is, okay, translation. Okay, so here you have an open interval, a to b, okay, and then you have a subinterval of the open interval, x1 to x2, okay, and then we know that f is differentiable on the open interval. So if it's differentiable, it has to be continuous. And so if it's differentiable on this open interval, then it's also differentiable on a subinterval of the open interval. It's differentiable there. And it's continuous on this closed interval, which is a subinterval of a to b. All right, so if you're majoring in math, this concept looms large. For engineers, maybe not so important to know this, or science majors, but for math majors, yes, you will definitely need to have knowledge of that. Okay. All right, so we have a restatement of the mean value theorem on an interval x1 to x2. Obviously, C is between the two numbers, so that's, again, just a repetition. What else? Slide 50. So f prime of x is equal to 0, so f of, okay, yeah. Oh, so just showing that the derivative of a constant is 0 using the mean value theorem. So if the derivative of f is equal to the derivative of g for all x in an open interval, then of course the difference of two functions is constant on the okay. Well, here's an important corollary. Okay, so we have a corollary, so I guess we should spend time going over this corollary because this has important implications too. Yeah, so let's take some time to do this. So if the derivative of a function is equal to the derivative of f is equal to the derivative of g for all x in the interval a to b. Now, before I go further, f need not be the same as g, okay? So if the derivative of f is equal to the derivative of g for all x in the open interval, then the takeaway is that the difference between f and g is constant on the open interval a to b. Okay, that is f of x is equal to g of x plus a constant, and c need not be 0 in this case. All right. So I guess this is the proof of it. So if we have f of x is equal to the big F of x is equal to the difference of f and g, take the derivative, set it equal to 0. Okay. Well, it's because we stipulated that this quantity was equal to 0 because their two derivatives are equal. And so by theorem, since we know that if the derivative of a function is equal to 0, then the function must be a constant, okay? Because the derivative of a constant is 0 for all x in a to b. So if the derivative of the function is a constant, then f is equal to f of x minus g of x is a constant as well. All right. Okay, what next? So there's a note here. Okay, so for instance, suppose we have f of x as a piecewise defined function here. The domain of the function is x such that x can't be 0, and yeah, f prime of x is equal to 0 for all x in the domain. Okay, fair enough. And what's the conclusion? So f is not a constant function. It doesn't contradict the theorem because d is not an interval. Because 0 is excluded from the x-axis. So in this case, what is d? So let's take another look at what d is. So yeah, so this right here is not an interval. Okay, it's actually a union of two intervals. Okay, so therefore everything, there's no conflict with existing theory. Okay, so what else? Okay, oh, and here's another interesting application. Going back to trigonometry. Remember when we proved trigonometric identities? Well, here's one identity that you could never prove from your trigonometry class. Prove that the inverse tan of x plus the inverse cotangent of x is equal to pi halves. Okay. So let's see how we can use the mean value theorem to derive this. So if f of x is equal to the sum of the two functions, then the derivative is equal to the derivative of inverse tan x plus the derivative of the inverse cotangent x. And of course that equals to 0. So remember, when the derivative of if the derivative of a function is equal to 0, then the function itself must be constant. All right. So from the theory, and so since the derivative of the two functions is constant, for all x, okay, for all x you can just plug in 1, okay, and it doesn't matter really what number you plug in. 1 is a convenient number because we know that the inverse tan of 1 is pi fourth, and the inverse tan of cotangent. And the inverse cotangent of 1 is pi fourth, and so But actually, you could plug in any number you want, and you'll still get pi halves. Okay, so interesting mean value theorem. So this will conclude the lecture for section 4.2. And don't forget your web assigned questions. All right.